Today we're going to start section 5.2 talking about acid-base solutions. This is an important thing where we look at basically how much does this acid or base dissolve in water, how is it related to its what's called the acid dissociation constant or the base dissociation constant. Basically we want to see how much are these substances dissolving in water. How well are they dissolving in water? In this video, we're going to do the first three examples. So here's example one. We have a solution that's 0.1 molar of hydrochloric acid. It says find the concentration of all species, the pH, the pOH, and the percent ionization. First thing, identify the type of a substance. And so we're talking about HCl, and this is where it's important for you to know the 8 strong acids. And HCl is one of them. It is a strong acid, and this is going to be helpful because it gives us a strategy. A strong acid dissociates 100%. So every hydrogen in this compound and all of the HCl's, all of the hydrogens are going to be useful hydrogen ions, and all of the chlorides are going to be chloride ions. So we're going to do something that we haven't done in a while. I'm going to start by writing the dissociation reaction with the purpose of making an ice chart, or an ICF, whatever you want to call it, where we have the initial, we have the change, and if you want to call it this one E, if you want to use ice, it's equilibrium. Or you could call it final, whichever you want to do. It's really not going to make a difference for the calculation itself. It's just the nomenclature. All right, so every species in this dissociation reaction has a column. And then we have 3 rows for all of these: initial, change, and final. So initially, what do we have? So we have 0.100 molar of HCl. And we're just going off the things the question tells us. We don't want to add any information to the initial. We just want to go with what they tell us. They tell us we have 0.1 molar HCl. There is no hydrogen, no chloride to speak of here. So the strategy, the strong acid dissociates 100%, which means the change, we're going to subtract out the initial amount, and that's going to give us a final or equilibrium of 0. There's going to be none of this HCl aqueous left. What's going to happen is all of it is going to become hydrogen ions and chloride ions in the same concentration, because for every one of these we get one of these. And so the final concentrations, 0.1 molar of each. Since this is a strong acid, this was a really easy calculation to make. So find the concentration of all of the species. So we want to know concentration of HCl. We want to know concentration of hydrogen ions. We want to know the concentration of chloride ions. And we also want to know something else that wasn't written here, but always important in an acid-base question. When you know hydrogen ions, you also know the hydroxide ions. It's important just to see it happening. Now, granted, if the AP exam doesn't ask you for hydroxide, don't waste your time. But for now, it's a good practice just to see how things are related. So concentration of HCl at the end, in the final, it's just 0. Concentration of H plus, here it is, 0.1 molar. Chloride, same thing. Now for the hydroxide concentration, we have to look at, remember the dissociation constant of water, where we had Kw equals the product of the hydrogen and hydroxide concentrations. And so we want hydroxide concentration and that ends up being Kw divided by the hydrogen ion concentration. So Kw divided by the hydrogen concentration. We know nothing about the temperature in this question, so we're going to make an assumption. Our assumption is that it's 25 degrees Celsius. Usually the AP exam is very good about specifying 25 degrees, but as a general idea, if they don't tell you the temperature, we assume that it's at 25 degrees. So Kw is a specific number, 1 times 10 to the minus 14th at this temperature, 25 degrees. And hydrogen concentration we just found. And so when we put this into our calculator, or really you could do it without a calculator. I'll show you how, because AP will probably make you do this on multiple choice. 1 times 0.1 is really 1 times 10 to the negative first. And so 1 over 1, just 1, times 10 to the, so we got negative 14, we're dividing, so we're going to subtract. Negative 14 minus negative 1. And so it's 1 times 10 to the minus 13. pH, it goes into the formula, negative log of the hydrogen concentration. This one you could actually do without the formula, because it's really easy to estimate, especially when the coefficient is 1 here. So 1 times 10 to the negative first, the pH is just 1. And if you put this into your calculator, it would tell you the same thing, but that's the shortcut way to do it. We have 3 different ways to figure out the pOH. You can do the negative log of this number. You could do the idea that these two together add up to 14. So 14 minus 1 is 13. The negative log of this in the calculator, or just looking at this exponent, it's going to tell us that the pOH is 13. So the last thing, the percent dissociation, here's how it works. Basically, what was the final concentration, or what dissociated over what was the original concentration. And for this one, it's 100%. It's a more useful calculation when we're talking about a weak acid or a weak base where it's not 100%. And this agrees with this thing we already knew, that the strong acid dissociates 100%. So looking at example 2, we have 0.100 molar, and this is calcium hydroxide solution. Same ideas as the last time. Concentration of all the species, find the pH, find the pOH, and the percent ionization. First, let's look at the type and the strategy. Calcium hydroxide is one of your 8 strong bases. And this is going to be helpful because, kind of like in the last example, it's going to ionize 100%. So strong base dissociates 100%. So let's write the dissociation reaction. Here's calcium hydroxide, and we are coming out with calcium ions and hydroxide ions. And you'll notice there's a 2 here. I balanced it. Columns for 3 species, 3 rows, initial, change, and final. Initially, we have 0.1 molar of the calcium hydroxide. Like I stated in the last example, they didn't tell us about anything else, and so we're not going to have anything. The change minus, it's going to dissociate 100%. Which means there's none of it left at the end. No calcium hydroxides as a single unit. But it is going to be ions. So these have a 1-to-1 ratio, which means if we dissolve 0.1 molar of that, we get 0.1 molar of the calcium. Now here's where the balancing comes into play. There were 2 hydroxides for every calcium. 2 hydroxides for every formula unit here, which means we have to have 2 hydroxides for every 1 calcium. If we dissolve 0.1 molar of this, it means we're going to have twice as much hydroxide. So we are going to have 0.2 molar hydroxide as the change. Here are the final concentrations. Let's go ahead and write these in. Concentration of calcium hydroxide, 0. Concentration of calcium is 0.1 molar, and concentration of hydroxide, 0.2 molar. So it's important that when a question asks you to find the concentration of all the species, that you don't just do the chart. You have to physically specify, this is the concentration of calcium. This is the concentration of hydroxide. The only reason here is that there is so much data in this table that you can't expect somebody else to interpret it for you. You have to spell it out like this. So from here, POH is really the easiest thing to find right now. And that's the negative log of the hydroxide concentration. And if you put this into a calculator, you could do it by hand, it's going to be somewhere in the 1 to 2 POH range, just as a guess. And so you put it in your calculator and it comes out to be 0.7. So 1 was not a bad estimate, but if your coefficient is something other than 1, you might consider putting it in the calculator. pH, I'm just going to say 14 minus the POH. So 13.30. And then the hydrogen concentration from the pH. So first, this is the AP formula for the pH. I'm going to figure out how to get H by itself, this hydrogen concentration. And to do that, you end up using the this is basically how you're going to work backwards. Most of you have the math skills to be able to do this without me explaining it more in detail. If you do need that, then we can talk outside of this video. And so the hydrogen concentration ends up being 5.01 times 10 to the negative 14. Very small number. Again, percent dissociation, 0.1 molar dissolved. We had 0.1 molar to start with. That's 100%. And that pretty well agrees with the strong base. Slight shift in example 3. We are looking at HC2H3O2. This is acetic acid, 0.1 molar acetic acid. Now, is it a strong base or a weak base? I would not have you memorize the list of weak acids or weak bases. There are literally hundreds of them. But there are only 8 strong acids, and if I know those 8 strong acids, any other acid is a weak acid. And I know that this is not one of my 8 strong acids, which automatically means it's a weak acid. So the strategy here is to use an ice chart and also the Ka, the acid dissociation constant. Sometimes the question will give these to you, like this one. It tells us that the acid dissociation constant is 1.8 times 10 to the minus 5. It's basically an equilibrium constant, but it's specific for the acid. So let's go ahead and take a look at it. Let's start with our ice chart. Here's our dissociation reaction. Initially, 0.1 molar of the acetic acid, 0 for the others. This one is different because it's a weak acid. It's not going to change by 0.1. It's going to change by something, which is X, although I don't really know what X is right now. We're going to figure it out. Hydrogen concentration, I don't know how much it's going to go up exactly, but if you consider that for every 1 acetic acid, there's 1 hydrogen. If this goes down by X, this is going to go up by X. Same thing for our acetate ion. There's 1 for every acetic acid. Acetic acid goes down by X, this goes up by X. And so our equilibrium here for the acetic acid is 0.1 minus X. For the hydrogen, 0 plus X, just X. Acetate, 0 plus X, just the X. Now here's where the equilibrium part of it comes in. We need the equilibrium expression. So we say that Ka, the acid dissociation constant, it's just an equilibrium constant, equals, and remember it was products over reactants. So the concentration of hydrogen times the concentration of acetate. And they both had coefficients of 1, so their exponents are 1. We can leave it alone. Over the concentration of the acetic acid. And we can plug in the numbers or the variables that we have. So the Ka was given to us 1.8 times 10 to the minus 5th. Hydrogen concentration is X. The acetate concentration is X. And acetic acid 0.1 minus X. This is going to make for some really complex math unless you do the shortcut. In chemistry, we assume that we use the shortcut. And when we get to the end, we're going to go back and look. The shortcut is not going to hurt us in our calculations that much. The effect is going to be something extremely small. If we could even tell the difference, we'd be using a supercomputer to measure our stuff and do the calculations. We wouldn't be doing them by hand. So here's the assumption. Look at this. This is a very small amount. Only 1.8 times 10 to the minus 5th, really dissolves. So most of this is going to be the acetic acid still, which means this is a very tiny number. Let's say it was 0.1 minus 0.001. If you were going to round it, it'd still be 0.1. And so the shortcut method here is, let's do this in green, to come over here and we say it's 0.1 minus X. I'm going to make my math a little easier. And that minus X is just going to disappear. So this went from a really complicated math problem to now this is pretty simple stuff. So, this is 1.8 times 10 to the minus fifth, multiply the 0.1 over, and we have x squared. So solving for that, multiply square root, and we're going to find that x is, here we go, 1.3 times 10 to the minus 3. So it's so small that it's not going to make a huge difference, because this number is really 0. I'm going to write this part down. 1, 3. And if you were to use the initial minus that, got there's 0, there's 10, there's 9, there's 7, 8, 9, 0. 0.987 versus, look at this number, and if we rounded this number even to 3 significant figures, 7 rounds up to 8, 9, and it's still 0.1. And that's how we can get away with this shortcut. And it just makes these calculations 1,000 times easier than it would be without the shortcut. And so we find the concentration of all of the species. Let's separate this off. Concentration of hydrogen is X, which is 1.3 times 10 to the minus third molar. The concentration of the acetate is X, which is 1.3 times 10 to the minus third molar. The concentration of the acetic acid was 0.1 minus X, which is 0.1 minus this number. I actually already did this one. It ends up coming to 0.099 molar. So then find the pH, negative log of the hydrogen concentration, and it comes out to 2.87, which is very approximately 3. And that's how you could estimate it. POH, I wouldn't spend a whole lot of time figuring out the long way. I would do 14 minus 2.87. We've got 11.13. Using this number, you could figure out the hydroxide concentration if it's required, and that would be 10 to the negative pH, which turns out to be 7.4 times 10 to the minus 12 molar. Exponents negative 12, very close to 11. This is where your percent dissociation comes in again, and you want to pay closer attention this time. The calculation is X, this number that we found, over the initial. And so X, we have 1.3 times 10 to the minus third, and the initial was 0.1. And it ends up coming out to 1.3%. So out of all of this sample, only 1.3% of it actually dissociates. The other 98.7% are still HC2H3O2 together, stuck together, and And so it's very little of it is actually dissociated.